Today we are going to talk about device-side memory model. By device, we refer to the OpenCL device that execute OpenCL kernel functions. On the device side, the memory space is classified into four primary categories: global memory, local memory, constant memory, and private memory. And we use keywords global, local, constant, or private to refer to these memory types. Depends on the OpenCL development environment, you may need to add __ in front of these keywords. We use this diagram to illustrate the relationships among these memory structures. This picture refers to the memory structures on the device side. As we can see that this global memory is visible to all the work items and work groups. As a part of the global memory, constant memory stores the data that are not being altered during the runtime. Within each work group, there is a small area of memory called local memory that is visible to all the work items within that work group. So likewise, you see another local memory in this work group, but this local memory is not visible to the work items in the other work group. Within each work item, we have a private memory space that's only visible to the corresponding work item. So this private memory space is not visible to these other work items, even though they are in the same work group. The memory structures follow such hierarchical consistency model. Within a work item, the memory operations are ordered predictably. Any two reads and writes to the same address will not be reordered by hardware or by the compiler. Between the work items and within a work group, memory is only guaranteed to be consistent at a barrier operation, and we'll explain what a barrier operation is shortly. Between work groups, there are no guarantees about memory consistency until the completion of the kernel execution. So you may not make assumption that the memory operations that you made in one work group will be visible to the work items in a different work group. Work items from different work groups cannot synchronize using a barrier. That is to say, barrier operations only apply to work items within the same work group. In OpenCL, there's no requirement for the compiler to make anything but last write to a given address visible outside a given work item. The memory spaces map to hardware as programming construct, and they are disjoint spaces. By default, the address space for function arguments and local variables within a kernel function is private. That means these variables are allocated in a private memory space. You cannot cast from one address space to another because that would imply either the data live in the global accessible address or the compiler would have to generate a copy to go with the cast. The image arguments, the image objects to a function always live in the global address space. The constant address space, described by using the constant qualifier, is used to cleanly separate small sets of constant values from the global address space in order for the runtime to allocate caching resources or other efficient constant memory banks if possible. Private memory refers to all the variables not declared in an address space qualifier, and all the variables within non-kernel functions, and all the function arguments that are not pointers. To declare an object in the global memory, you will use qualifier __ global or simply global or image types. And data in the buffer object can carry any scalar data type, vector data type, or user-defined data type. Let's look at this example. We have a for loop, and that is to copy the values from one array to another array, but with some offset. So what we're doing here in the OpenCL code is first we define a structure which has two floating point variables. And we define a kernel function, and that's taking one argument, which is the input-output buffer that's allocated in the global address space. Note that we use this A structure to define the data structure type of this buffer object. And within the kernel function, we use this customized data structure, A structure, to interpret the pointers used to point to the memory objects in the global memory. So this line of code is trying to use the global ID of this work item and use that as an offset to the input-output buffer pointer, and then we will retrieve two floating point numbers. The reason we retrieve two floating point numbers is because we use this data structure which consists of floating point A and B. And also, next line for the output location, we use these buffer pointer and the global size, which indicates the number of variables in this dimension, and also with the global ID. So what we're trying to do here, the next two lines, is to use the input location to retrieve the first floating point number in that data structure and perform the operation, and then use the other variable in the data structure to update the value in the output buffer. Local memory is a small scratchpad memory on device, and that is different from DRAM, which is typically off the chip. Local memory is often accessed with separate memory operations on the device, and it may incur direct memory access or memory-to-memory copy operations. It is very efficient for communication between work items in a work group. In this kernel function, which is called local access, this kernel function takes three arguments, and two of them are pointers to global memory, and the third one is a pointer to local memory. Within the kernel function, we first allocate a floating point variable in local memory. We call a local array with one element. And then we initialize the element with these values from the input global buffer. So we take a of 0, assign the value to this local variable in this local array. And then we use the output, we use the other local memory, C, to keep a copy. Then we retrieved another variable from this global memory, buffer A, using the global ID as the index, and we copy the value to this location in the local memory. And note here, the C is the variable that's allocated in the local memory space. And then we have a workgroup barrier instruction. We use local memory sense as the argument. This statement essentially to sync all the work items within this work group up to this point. So none of these work items can proceed until all the work items have finished these first several lines. And after that, we will perform a addition operation using this element in the local memory space for C, and add that to another variable in a local array. If this work item is not the work items with ID 0, then we'll perform these additional operations. So this diagram illustrates basically what we had in the previous OpenCL kernel function. We have two buffer objects, A and B, which are allocated in global memory space. And we have a array C allocated in local memory space. This A local array is a one element array, or just single variable, that is also allocated in the local memory. What we are seeing here is upon the start of this kernel function, all these work items within this work group will first execute the instructions before the barrier instruction. So these operations will try to use the values from A to initialize this A local array. And until the initialization is done, none of the work items can proceed to perform the addition and writing to the value to the buffer B. So this horizontal line here represents the barrier operation to synchronize all the work items within this work group. And after that, the work items will perform additions by using this single variable with the corresponding values in this local memory, and perform the addition operation and update the corresponding locations in the result buffer B. And this whole thing is performed within one work group, and you can imagine that there will be other work groups will perform the same thing, but essentially on different part of the input data and output data. Fence is another operation that can allow communications between work items within and between work groups. But we have to know that this fence operations, they do not guarantee the ordering between work items. Instead, the fence operation ensures that the load and the store issued before the fence will complete before any load or store instructions issued after the fence. This is not to synchronize these work items. Instead, it just performs a ordering on the memory operations that's issued by these work items. And the APIs for fence are as follows. You can use read memory fence to perform controls on read operations, or write memory fence to control the write operations, or just generally using memory fence. You can use two flags to specify which address it is fencing. It could be local memory or global memory. Again, we said earlier that fence operations are used to provide ordering between memory operations of a work item. And its sole purpose is to ensure the loads and the store issued before the fence will complete before any loads or stores issued after the fence. There's no implications of synchronization by the fences alone. Let's look at the example of memory fence. Let's say we have a kernel function that tries to compute the sum of n floating point numbers. So each work group computes a subset of n numbers, and we want to use work item 0 to store the result into the global memory, And also we used work item 0 to increment a counter to indicate which portion or how many parts of the floating point numbers that we have completed performing the sum operation. Let's say the kernel function is called sum. It takes several arguments. Array and result are the input data and output buffer respectively, and we have a n to determine the number of floating point numbers we need to perform the sum operation, and this count is the counter that will record how many of them have completed. The first statement, partial sum equals calculate partial sum array n. Let's assume that this calls another function to perform the summation operation on a subset of n arrays. And then we use get local ID 0 to find out whether this is the work item 0. If this is the work item 0, we want this work item to store the partial sum to the global memory. So we assign this partial sum into this location within the result buffer. Note that this is in the global memory. And let's ignore this memory fence instruction for now. After this assignment to store the partial sum into this result buffer in the global memory, we will increment the counter in the global memory to say that this work group is done. Now, this assignment instruction, this line of code will be translated into a write operation to the global memory, whereas this line of code will trigger an atomic instruction on one of the variables in the global memory. So if we do not have fence instruction here, it may happen that the order of these two instructions will not be guaranteed. So it may happen that the increment instruction happens before before we putting the partial sum into the result. With the memory fence instruction, we basically guarantee that the assignment to the result happens definitely before we incrementing these counters, and that's exactly what we expect to do. Barrier operations support a read-write fence in one or both memory spaces, as well as blocking until work items in a given work group. We saw an example of barrier instructions before, where we have all the work items have to wait until none of the work items in a work group can proceed until all the other work items finish reaching this barrier point. And atomic operations are also helpful in guaranteeing that a write update occurs, but also that read and write combined with some operation on the data occur without interruption. And this is very important in incrementing counters and to exchange the value of variable with the memory location, because oftentimes these are complex operations involving both read and write operations to the memory and also some arithmetic computation. And our goal is to guarantee that these operations will be completed atomically. Images differ from buffer in several ways. They are opaque types that cannot be viewed directly through pointers. They are multi-dimensional structures, and they are limited to a range of types relevant to graphics operations, and they cannot be used to freely implement arbitrary structures. The reason we have image objects in OpenCL is to offer access to special memory functions, and that can be accelerated using graphics processors or other specialized devices. And operations such as filtering can enable efficient transformation of the image data based on the collection of pixels. For example, there are cases we use z-order to manipulate the text maps and to increase the spatial locality of reference during texture mapped rasterization. With this z-order, we can basically group these neighboring pixels or regions of pixels into one cache line and to represent rectangular tiles so that increase the probability that access to the nearby pixels or regions. And also at the same time, it decreases the probability of costly page breaks, for example, changing the roles in SRAM or DRAM. And it's very important for image operations because, for example, the 3D rendering involves arbitrary transformation, rotation, scaling, and these z-order axes can drastically improve the way we utilize the cache, which is much faster than loading the raw data from memory again. Pipes are proposed in OpenCL 2.0. The goal is to capture the execution behavior of streaming applications. There can be multiple kernels working in parallel over a sequence of data. We call them streaming data. And this will improve in application throughput and by overlapping execution and data exchange. The support of pipe semantics can be different from device to device. On FPGAs, because of its reconfigurability, implementing pipes is simpler. On GPUs, because there's no pipe structures built in, so it'll need to offload data on global memory, which is off-chip. As a result, it actually minimizes the potential of overlapped execution. Let's look at this example where we use an execution flow to detect objects in pictures. The kernels are pixel smoothing, which is a set of 2D filter for Gaussian pixel density smoothing function. And another stage is the mixture of Gaussians, which subtract foreground pixels from background pixels. And then the third stage is erosion, which calculates the minimum value from neighbors of a pixel. And the final stage is dilation, which is to calculate the maximum value from the neighborhood of a pixel. And the figure below shows how these pixels and the intermediate data that's computed and transferred from one stage to another stage. Essentially, these intermediate results, for example, coming from the pixel smoothing, we have smooth pixels those will be inputs to the mixture of Gaussian stage, and these foreground masked pixels will be sent into erosion, and then the foreground scenes clean up. After the foreground scene is cleaned up, the dilation stage will calculate the maximum value from the neighborhood to generate to detect the objects. With pipes, we can perform very efficient in-kernel communication. Pipes are essentially a type of memory object that is used to maintain data in first-in, first-out order. Pipe is created and instantiated by host, and pipe stores data in the form of packets. It restricts only to kernels on the device, so it's not to be updated or accessed by the host after it's created. There are several pipe-related APIs: read pipe, write pipe. For example, in this diagram, we show a pipe memory channel that connects to a producer kernel to a consumer kernel. And we have an intermediate data buffer that could be in global memory. What we're sending in this example, what we send through the pipe is the offset to the data buffer, or called the tiles. So we use this TID to represent the offset to this buffer, and the pipe will be used to transfer the sequence of tile IDs or offsets from the producer model to the consumer model. As a result, instead of sending the actual data, we're just passing around this offset from one kernel to the other kernel. Without using pipes, so what's going to happen for this 4-stage pipeline is shown on the left side in the sequential scenario. We have the CPU and the FPGA device. In order for the pixels to pass from one stage to another stage, what's going to happen is at each stage, the data will be read from the global memory, processed, then stored back to the global memory. Then the next stage, the intermediate result will be read again from the global memory, processed, and stored back to the global memory. And we do the same for the ERO stage and DIL stage as well. So what you can see is there are a lot of memory operations performed towards the global memory. Read, write, read, write, read, write. Even though we have these 4 stages of processing, all these 4 kernels are competing the global memory for accessing the immediate data. And that's the issue of this sequential scenario. There's a lot of latency incurred due to the individual kernel execution and multiple memory access to the global memory. In contrast, with pipes, what we can have is the first stage, SMT, will read the original pixels and process them. The intermediate data will be sent to the next stage through these kernel pipes. As you can see, these pipes are on-chip memory structures that can transfer these immediate data from one kernel to another kernel efficiently. And we do the same thing for the next several stages. All of them are using pipes to transfer the immediate data. And in the final stage, after the DL stage is done, the object detected will be stored into this global memory. So as you can see, compared to the sequential scenario, the memory accesses to the global memory reduced drastically.